Okay, welcome everyone and thanks for joining us today. My name is Matt Willard and I'm the Senior Marketing Manager at Fluence Analytics. Before we start the webinar, please note the chat feature at the bottom of your screens. You can use this to make comments or pose questions to our panelists during the webinar, and Mike will respond to your questions at the end. Fluence Analytics is a startup headquartered in New Orleans, Louisiana that spun out of Tulane University in 2013. We manufacture industrial and laboratory monitoring solutions that produce continuous data streams and enable real-time optimization. This leads to improved process control and faster R&D. Today's webinar will overview the range of detectors incorporated into ACOMP that enable real-time monitoring and characterization of polymerization reactions. Our panelist is a co-founder and the CTO of Fluence Analytics, Mike Drenski. And at this time, I will turn the webinar over to Mike.
All right, thank you, Matt. And again, I'd like to thank everyone for attending and appreciate your contribution to us. And hopefully we have a good webinar today. All right, so first off, we're going to discuss what we're talking about today. So we're going to state the problem, discuss a little bit about the solution, that's the ACOMP technology itself. And then we're going to go into the guts of the presentation and how it's done, the principle of ACOMP, the detectors, analysis of each of those detector signals, and then further interpretation of that. Once you have all that data that you've collected and done analysis on, you can start to use it more exciting ways to do active control of polymerizations and other things like that. So we'll show some examples of that later on in the presentation. And then we'll discuss a little bit more about additional detectors that were not covered in extent in this presentation, but we'll discuss them a little bit in some of the outlooks for later detector integration for ACOMP itself. All right, so what is the problem in the industry? In typical laboratory analytical measurements for polymerization, either batch or continuous processes, somebody goes out and grabs a sample and runs it off to the laboratory to do an analytical measurement on. This could be either characterization of the molecular weight, viscosity, or Mooney, or something like that. But the real problem is that there's inefficient monitoring of this process. So you get one data point typically on every 30 minutes, once an hour, and we've actually seen cases where it's gone up to 12 hours per data point. Leads to a very inefficient reaction control of the process. Some of the problems with this is intermittent or even no data collection that can help you control the process. You usually end up with either off-spec, poor control, quality deviations, or reduced efficiency. Now, there's a lot of things going on in the process and a lot of things that the engineering world is doing to mitigate all these problems. So I'm not saying that this is rampant in the industry, but there's always obviously ways that this can be improved. And that's where we bring the ACOMP to the table. So with ACOMP technology, what we do is we actually take the sample stream directly from the process. We collect the data, send it to analytics and analysis software. That information is then sent directly to the plant control room. The person that's controlling the process directly, he can then make, or she can then make control decisions with improved reaction control. So then they can actually say, okay, this is what we're making right now. How do we want to manipulate the process to either produce a better quality product or change from one grade to another product or something along those lines. And this is all can be done because we're producing data in a continuous stream, feeding it directly to the person that's making the decisions from there. Now, some of the benefits from this, cost, efficiency, quality, health, safety, and environmental concerns. All these are direct correlations to having direct and continuous data from the process. And that's really what the industry is trying to go toward these days, is to have more information about what's going on so that people can make decisions about how to make it better. Down the road, we like to, take all the decision making and turn that into true control process analysis and things like that, so that the process really runs itself based off of continuous variables, how they're being changed, and how they can be manipulated in real time by like a continuous feedback process. So we're going to talk a little bit about that really late into the polymerization and the presentation today. So let's discuss a little bit about how it's done. So first we'll start off with the ACOMP principle. Obviously there's a polymerization taking place in a reactor somewhere. The ACOMP then takes a continuous reactor sample somewhere on the order of maybe 50 microliters up to 2 milliliters per minute. And this is a continuous stream of sample that's coming out of the reactor and going to our measurements analysis devices. As I mentioned, it's a continuous measurement. There's a delay since you do have to take sample from the process and get it to the detectors. Somewhere on the order of 30 seconds to maybe 300 seconds, 5 minutes or so. This is substantially lower delay than you would actually have if somebody were to go out there with a bucket, take a sample from the process, run it back to the laboratory, and then have to do all the manual makeup of the sample from there. I do want to point out this is data collection is done continuously at 1 Hertz. And then we also want to point out that the ACOMP doesn't need chromatography columns to make measurements here. And this is one of the bigger sticking points in the industry, is understanding how these measurements can be made in real time without having to do size exclusion chromatography on the samples themselves. So once the sample comes out of the process, it goes to the front end of our ACOMP system where we do the quenching, diluting, and conditioning of the sample. And this is really where it takes somebody, typically they'll take the sample and do a bench makeup of it, dilute it, get it down to the concentrations that it needs to go into some analytical device. Our typical analytical devices are kept in what we call the back-end detector train of the system, and that's generally intrinsic viscosity, light scattering measurement, UV absorption, and differential refractive index. We do have some optional detectors that we've worked with in the past. They're not off-the-shelf detectors that we stick right into the ACOMP, but they're more for niche applications where a customer might have some interest in some of these measurements, and we'll work with them to develop a particular solution for that particular case. But what we're going to talk about today in this presentation are the standard sets of detectors. So once you collect all this data, it goes through our analysis packages. And if you look up on the right top corner there where the monitored characteristics, we get molecular weight, intrinsic viscosity, composition, conversion, ppm, residuals, and then detection of process anomalies, because you actually have a continuous stream to tell you, hey, something happened in my process. Maybe a pump started to fail, or maybe my heat exchanger is not working the way it should be today. So therefore, my polymerization is not carrying through the way it's expected to. So let's jump into the meat of the presentation. Let's talk about the detectors. That's why we're here today. So our standard set of detectors, we've worked on a set of detectors on either sourcing or developing proprietary methods and means to produce detectors that are meant for ACOMP measurement. These are similar to the types of detectors you might see on a chromatography system with light scattering and viscosity and refractive index, but they're more designed for a continuous process that's being used in industrial applications. We have built-in temperature control to eliminate sensor drift, because if a sensor or detector like this is put out into an industrial environment where the temperatures can change quite drastically, we want continuous and clean data from there. As mentioned, these are similar to, but not quite like the analytical detectors that you would see in a laboratory. So we have larger bore paths to eliminate plugging and fouling of the instrumentation. And we'll talk a little bit more about the nice part about the fact that ACOMP always cleans itself during polymerizations and after polymerizations as well. I do need to point out that not all detectors are necessary for every application. If there's cases where you don't need light scattering, or cases where light scattering is not applicable, we won't produce that, or we won't need to put that instrument into the ACOMP system. So we can tailor the ACOMP system appropriate to the chemistry we're monitoring. Now the 4 sets of detectors we're going to discuss, there's concentration detectors, differential refractometer, UV absorption, we'll discuss those later. And then we also have our molar mass detectors. And this is mostly what people are looking for, is the dilute solution viscosity or the molecular weight for multi-angle light scattering detection. All right, so let's talk about what ACOMP data looks like. So typical ACOMP data, if you look at the beginning of a polymerization, say in this case a batch polymerization of a terpolymer of methyl methacrylate, butyl acrylate, and styrene, you can see in the beginning of the polymerization, the concentration detectors are responding to the monomer concentration that's added to the process. So we see the refractive index go up, we see the UV absorption going up, and that's because the double carbon bond is absorbing light, so therefore the absorption goes up. Refractive index changes because the monomer has a stronger index refraction than that of the background solvent that we're monitoring it in. Now, we notice that the viscosity and the light scattering detection do not change because there's no molar mass yet. We're just looking at monomer going through the detector system. But as the reaction starts, we see the detector trends changing in real time. As I mentioned before, this is data that's collected at 1 point per second. So throughout the entire process, you can see individually 1 point per second coming across your detector stream and telling you what's taking place in real time. Now, if we notice the UV absorption drops, and that's because those double carbon bonds from the monomer are clicking open and being clicked into a polymer chain, so they no longer absorb light. In this case, the refractive index goes up because the polymer has a higher dN by dC than the monomer itself in the background solvent. But the nice part here is that when you see the polymerization taking place, the molar mass is increasing. So the light scattering and the viscosity measurements giving you information about the molar mass and the architecture of the polymer itself. So this is, again, collected all in continuous and real time. So let's talk about how each of these detectors work, the principle behind them, and go forward from there. So we'll start off with the differential refractometer. The idea here is that it's measuring the differential change of solution index refraction with respect to the concentration of polymer. So as the polymerization is taking place, you're converting monomer to polymer. The system and the detector is actually seeing that change of index refraction as the polymer concentration is increasing because monomer is going down, polymer is going up. So that divergence of the beam path directly translates into a voltage signal or a refractive index signal that we collect from the detector. So to perform analysis, what do you got to do? You collect your solvent and your monomer baselines of this batch polymerization. There's certain things you must know, the dN by dC of the monomer and polymer, dilution factors, and calibration of the instrument. From there, you can calculate the monomer concentration, determining the polymer concentration by mass balance of monomer converting into polymer, and then also calculate the conversion of the process from 0 to 100% conversion. The equations are pretty straightforward, and we're not going to go over these in detail throughout this presentation. You guys will all have access to the presentation, so you can go through and work them out yourself if you feel an interest, but they're all here for you. But the basic idea is that there's not a sophisticated amount of analysis taking place. There's a number of constants in play, and then continuous detector streams that we're collecting from the samples themselves. So in this case, we show that we can get the concentration of monomer throughout the process by simply monitoring the refractive index change as the process takes place. And as I mentioned, having a few constants like the dN by dC and the calibration factors of the system, you're all set to collect all the data you want. Once you know the monomer concentration, as I mentioned, you can calculate the polymer concentration, you can calculate the conversion of the process, and that's usually the information that you're looking for from these concentration measurements. Now, an interesting aspect, let's show a use case example of why index refraction is kind of exciting to monitor during a process. Here we're looking at a step growth polymerization. These polymerizations are typically on or off. So it's going very slowly and all of a sudden it kicks on. The nice part about using the refractive index in this case is we can actually see the very early buildup of oligomerization. So in this case, we saw the monomers coming together, sticking into essentially about 10. Once you get the oligomerization much beyond that, you can see the viscosity in this case shoots up, and because that's the polymerization going off. So nice information about the process that you can gain just directly from the refractive index of the monitoring in real time. All right. So now let's look at the UV analysis. It's another concentration detector. So what needs to be done to produce concentration from UV analysis? So again, you need to collect your monomer and solvent baselines, and we're going to take those values and calculate the extinction coefficient by the Beer-Lambert law. Once you have that, you can use the extinction coefficient, plug it back into the equation, and calculate the monomer concentration throughout the process, again, as your monomer is converting into polymer. Again, by mass balance, you can calculate the polymer concentration and conversion from there. So what's the principle of this? You have a light source, monochromatic, a light source that's going through the detector system, a monochromator that then splits the white light into the different wavelengths of interest, and then it flows through the light goes to the flow cell, and whatever absorbs that light is then detected as a difference between the initial light source and the sample light source. So as I mentioned, what we're looking for is the extinction coefficient initially. So once you put the monomer in the reactor, and before any polymerization takes place, you know the concentration of the product in the reactor. So we can get the extinction coefficient from that, and as you can see, the equation can then just be turned around on itself to use the now known extinction coefficient to calculate the monomer concentration. So that monomer concentration can then be calculated throughout the entire process as again, monomer is converted into polymer. The equations from here are very similar to those shown for the reactive index. We get the monomer and the polymer concentration of the polymer to the detectors, and then the conversion again. So as I mentioned, these are the values that are typically of interest with your concentration detectors. So now you can take those concentration measurements and plug them into higher level analysis, as we mentioned, get the molar mass and in the intrinsic viscosity of the product that you're actually producing. In this case, what do we got to do to calculate intrinsic viscosity of our product during the polymerization as the chains are growing into, small polymers or large polymers? So we want to see that in real time. So idea is here we got to calculate and collect our solvent, monomer, and zero flow baselines. These are pretty straightforward at the beginning of the polymerization, as I showed with the detector data on one of the previous slides. You need to then figure out what the difference is between our solvent baseline before any polymer is being produced to that of the polymer being generated. And then using the concentration from either the refractive index or the UV absorption, we can then calculate the intrinsic viscosity of the product that we're producing. The idea here is we're using a very simple principle of Poiseuille's equation. So the pressure drop across a single capillary as the flow is held constant, we can see that the difference in the background solution viscosity with the increase in concentration of polymer is the intrinsic viscosity. So as we approach lower and lower concentrations, we actually get the intrinsic value of the polymer viscosity. Now the interesting part of here is this is actually a macromolecular property of the polymer itself as opposed to a bulk solution property of, say, viscous polymer solution. So the idea here is instead of figuring out what the viscosity of the product is in the reactor, you want to know the viscosity of one individual molecule and how much that changes the solution viscosity that you're measuring it in. And the way you do that is you collect the data directly from the sensors. So if we look here, we see the reduced viscosity in this case is equal to the polymer viscosity minus the solvent divided by the concentration and the couple parameters from the measurement itself. And as I mentioned, as the concentration approaches zero, you instead of having millions of molecules, you go down to maybe one molecule. The idea here is that the reduced viscosity approaches intrinsic viscosity, and that's usually what people are looking for. If they take a sample and inject it into say a triple detector GPC system, they want to know the viscosity, the intrinsic viscosity of the product that they have produced. All right, so now that we have the information, there's a little bit of extended information you can get from this as well. So once you have real-time viscosity value, you can then interpret that into the viscometric molecular weight, since it's a macromolecule property of the polymer itself. Now, you need to know the K and alpha parameters of this particular chemistry or this polymer itself in the solvent. So these are values that you can either look up in literature, or there's methods to actually calculate these values offline, not necessarily with ACOMP, but once you have those numbers, these values can be plugged in to calculate their molecular weight directly from the viscosity value itself. Now let's look at a use case of this where we're both using the UV absorption and the viscosity measurement to look at a couple of properties of the polymer that release basically the spec of the product that the customer is trying to produce. So in this case, we're monitoring in the blue stream the UV absorption as it's dropping down. So that's the monomer concentration. In this case, there's a residual monomer spec that they need to get to pass FDA regulations before this product can be dumped from the reactor and sold as a product to their customers. So the idea is here we're monitoring in real time. We can actually take the kinetic value of this product and the UV absorption and determine exactly when they're going to reach the spec that they want to. And the idea here is that, based off of typical SOP, the customer would then use the SOP to stop the reaction based off of historical knowledge about, if we cook it this long, we're going to be safe. But with ACOMP, what we can find out is that you can shave off quite a few hours of cooking time if you actually know in real time when that sample is done. So in this case, we shaved off about an hour and a half of the process time and showed the customer that they can take their product and dump it and then give it to the customer or send it to a post-holding tank or something like that, a blending tank or something of necessary need, much sooner than they normally would. And the idea is that, the cycle time reduction here is, quite costly if you leave your product in the reactor cooking, saving valuable time and space that you could be starting to produce more product from. If we looked at the viscosity signal, we can see the purple increasing, and that's a reduced viscosity, or as I mentioned, the intrinsic viscosity as the correlation there. The idea is that if you're producing a product of specific viscosity and you're sitting there cooking it, beating it up with your pumps, you're recirculating through the system, you can start to degrade the actual product of interest. And in this case, we saw that over that hour and a half of time, we can see that the reduced viscosity is decreasing. And that's just a matter of shearing the product, stressing it to the point where you're breaking apart the chains that you went to all this effort to actually produce. So using real-time analysis and real-time data on the system, you can say, we got the product we need, we've reached the residual monomer spec, let's dump this out and then start a new batch of product and then make more money. All right, so cost savings, impressive. All right, so calculating molecular weight. So we have the fourth detector in there, the static light scattering measurement. So the idea here is we want to get the molecular weight, and in other cases we can actually get the reduced or the radius of gyration as well. Simple measurement is, again, monitor the process in real time, get your monomer baseline prior to polymerization before any polymers are actually produced. And then you're looking at the difference in signal between the monomeric form and the polymeric form. Calculate the normalized intensities of static light scattering from there, and then plug all those values into the, well known to me, but maybe not everyone else, the Zim equation to calculate the Rayleigh ratio of scattered light scattering with respect to the polymer concentration over time. Now, once you plot this into the Zim plot, you can get the intercept to calculate the molecular weight, and then the slope can actually be determined into the radius of gyration. So how does this work? We have a multi-angle static light scattering system from our, we've developed in-house. The idea is it's designed for ACOMP applications. It's not a light scattering detector that you would have on your GPC system. One of those detectors would probably foul up or break or, would not work in this process. So we've developed something specifically for the use case of application for ACOMP itself. It is a 5-angle measurement device, and as I mentioned, the interpretation of the Zim plot extrapolating out to the 0 angle can give you the molecular weight and the radius of gyration from that data. Again, we're not going to go through all these equations and the constants that go along with them, but they're here for your reference if you need to look at them. But the idea is we're measuring the real-time intensity of scattered light from the product as it's being produced. Now, from this information, the bigger the polymer gets, the more light it scatters. So we can actually see that intensity of light increasing over time. Once we know that intensity of light, we can plug it into, as I mentioned, the Zim equation. And here we can see that the intensity of light is directly proportional to the molecular weight with respect to a couple of other parameters. In this case, the optical constant, as well as the concentration of the sample that we're measuring. So in most cases in the ACOMP application, we want the concentration to be very low, so we're not looking at intermolecular interactions where you have a high concentration of molecules interacting with each other in second and third scattering instances. So we want to dilute the sample down to a concentration that's appropriate for measurement. So again, here's some more constants, just defining them for the end use. But here's the interesting part. So once you have this Zim plot, you're generating this in real time. What we can look at is as we take this scattering angle, the scattering vector, and approach to 0 scattering angle, we can actually see that the intensity of light is directly proportional to the molecular weight. So there's where you get your molecular weight. That's the y-intercept of this particular graph that we show here. So molecular weight is very simple and achievable by this measurement. The interesting fact also is that if we take this same equation and look at it a little differently, the y-intercept plus equals the mx plus b, so the slope of this plot actually reduces down into the z average mean radius of gyration. So the slope of that plot that we just showed on the previous screen here can give you the radius of gyration of your molecules. So it's another interesting aspect that most people are interested in. If I produce a polymer of a molecular weight, what is the architecture and space dimension that it takes up? So these are two simple pieces of information that we get directly from our measurements in real time as the product is being produced. Now, there's an interest, as I mentioned, what happens in the case of a high concentration polymer, or in other cases where you have a viral coefficient that's very strong. If we look at this equation back here, where the viral coefficient is shown at the back end of there, if this is not at a low concentration, so you reduce the viral coefficient to 0, or if there's a high concentration or a high viral coefficient effect, what we can do then is take the values, plug them in, and then correct the molecular weight based off of those known parameters. So we can get the corrected value from this, and we can deal with other cases where it might not be feasible to drop the concentration down to values where we can actually get this viral coefficient out of the way. So these are all things we've thought about, we've worked on for quite a few years, and developed and processed and published quite a few analyses on these in the past. So, all right, some of the interesting aspects of using the light scattering data. In this case, we're looking at the onset of gelation, not necessarily the direct molecular weight, but the light scattering instrument is very sensitive to the formation of high molecular weight species. So as these monomers are clicking into polymer chains, we see the molecular weight building up. But in the instance here, we can see on the right graph, the molecular weight's building up over time, but all of a sudden there's an inflection point. This is where the polymers then start to interact with each other and start to gel up on you. And this is obviously a bad thing in the industry, because if your polymer decides to gel in your reactor, you can have some downtime. There's a lot of maintenance, a lot of cleanup, disposal of waste product that you're going to have to deal with here. So real-time and continuous measurement of light scattering in that case could tell you, hey, something's happening. You need to adjust the process to eliminate the aspect of gelation that's taking place. The nice part is, even though the gelation event's on its way, light scattering picks it up much sooner than you would actually see with any other viscosity measurement. And that's because you're looking at independent and direct molecular weight changes over time. So, all right. Now, with all this information that we've gotten from the detectors, rather than just look at that and figure out what's going on, let's use that information to actually do active control of the polymerizations of the reactions themselves. So what do we get from the typical analysis output? On the left, we see the concentration. So there's polymer concentration, monomer concentration, and those can be interpreted into the conversion of the process itself. With those two values alone, you can do control of the product that you're producing. Say a semi-batch process where you want to feed in monomer at a specific rate to keep your ratio of monomer to initiator constant to produce a constant molecular weight over time. So if we use that information, you can go forward and control the process there. But if we look on the right side of the graph here as well, we do have the molecular weight intrinsic viscosity values directly and continuously throughout the process too. So in the case where you might have a molecular weight that's drifting off from a spec, you can then go in and feed the monomer and control the process to bring your molecular weight on spec the way you want it to be. All right. So here's a couple of examples. In this case, we actually show our feedback control of the system. So in the laboratory environment, we actually worked out a way to control the concentration of the process as a polymerization was taking place. So as the polymerization takes place, in this particular case, a free radical polymerization of acrylamide, if we look at the red line on the graph here, this is what normal batch polymerization should take place. Your molecular weight should start up high and then decrease over time. Your concentration starts high and then decreases monotonically into a concentration value as you convert monomer to polymer. What we like to do in this case is show the aspects and the control features. But what we did is actually modeled the feed batch conditions to a sinusoidal wave. This is non-realistic. Nobody would really be doing this in the industrial environment, so we were just showing that this is possible in real time. Now, keep in mind, the polymerization is taking place all the time. So the monomer is converting into polymer, but we are actually able to feed the monomer into the reactor continuously to produce this sine wave concentration effect. Now, it might not be so obvious and easy to see for everyone, but the idea is here, the blue line is our monomer model, and then the black line is our actual concentration throughout the process. And we actually did pretty well. We got within a 2% error bar of monitoring and controlling the concentration. That information then can be used to build up, higher level calculations from there. So since we're monitoring the molecular weight in real time, we can actually determine the instantaneous molecular weight. What that idea is that each second you're producing a molecule of a specific molecular weight. So you can use that information to control the end product molecular weight of your process. The equations are here given on the side, but ideally the molecular weight is the differential of a real-time molecular weight over the fraction of conversion from that. So using that information, we showed in this particular case where we can actually drive the molecular weight up linearly. So similar to a controlled polymerization where you're growing the molecule in continuous fashion to get longer and longer chains over time. But this is actually a free radical polymerization that we just controlled. So the idea here is, as I mentioned before, in a free radical polymerization, your molecular weight should start high because there's abundance of monomer to convert into polymer. But as that monomer is then converted, you have less and less monomer to turn into polymer, so your molecular weights get smaller and smaller. But in this case, we actually fed monomer into the process and controlled the process, so we got bigger and bigger molecular chains. The nice aspect of this is if you have a target molecular weight that you're trying to achieve, you can drive the molecular weight to that value and then stop. Then you can say, okay, we've reached the molecular weight that we want of this product. We're done. We can then take this product and sell it. So the idea is what you can do with ACOMP, as I mentioned, control the polymer molecular weight and intrinsic viscosity with the monomer initiator feeds, control the molecular weight to arbitrary targets, in this case, counter to its normal evolution. Going extent from there, as I mentioned, since you know the molecular weight instantaneously as it's being produced, we can then bin those values up and produce what we call the molecular weight distribution as it's being produced. So as I mentioned before, ACOMP does not require chromatography to calculate the values. But what we can do is we can produce values that look very similar to chromatography values. In this case, as I mentioned, we monitor the molecular weight throughout the process of a polymerization. We bin them up and created a histogram, and then use that information to produce what we call a non-chromatographic molecular weight distribution, and then actually compared it to a GPC aliquot. So the same exact sample that was produced during that process was taken, injected into GPC, and you can see how well these two data sets overlay from each other. So this is not necessarily to offset GPC, but this information can be gathered in real time during the polymerization process so that you can actually make sense of what's being produced. Is it going to be spec after you produce the product, and then try to meet your specification sheets. So as I mentioned earlier, we're going to discuss a couple other detectors that are not necessarily in our base ACOMP package, but we do have experience with them. We have interest in developing them and working with customers in niche applications, so we'll discuss those briefly. We have worked quite extensively with pH. The idea is real-time measurement of the reaction parameters. So if your process is pH sensitive, there's no point in not monitoring that in real time. But if you want to monitor how the pH of the process affects molecular weight, reactivity ratios, the viscosity and conversion, it's quite applicable to using ACOMP in that case as well. Again, conductivity, same type of thing. If you're producing a process or a polymer that's either producing a polyelectrolyte or is very sensitive to the ionic strength of the solution that it's in, it's nice to know the polyelectrolyte effects and the ionic strength of the process as you're producing the polymers themselves to see what happens when the effects of those parameters change. Polarimetry was a nice niche application we worked with, was characterizing carbohydrates, polysaccharides, and concentration of byproducts and waste products. This is actually more of along the lines of finding out how much product is going to waste because they were not converting it into the actual converted polymer that they wanted. We do have some experience in actually IP in characterizing particle size, in this case by me scattering. In this case, the idea was looking at the droplet or particle size and inverse emulsion or emulsions or inverse emulsion processes where you're producing either hard particles, in this case, either beads or something like that, or in other cases where you're doing an inverse emulsion where you're actually working around the idea of your polymerization is taking place in these little droplets. So you want to produce droplets of appropriate size so that you have good activation of the monomers and initiators within them. We do have a little bit of experience, and we're working a little more with this idea is the infrared and near infrared spectroscopy. The idea is that in some cases where you don't have absorption, or if you just want more information about the process, you can use infrared spectroscopy instead of UV. Idea there is, again, you can get the concentration monitoring of the process in real time, but also you can get the reactivity, composition, distribution, branching, and some physiological parameters of the product that you're producing in real time as well. So these are, as I mentioned, a set of detectors that we have experience with. They're not offered in the current ACOMP base package, but we're very interested in working with customers to, see how these applications can unfold. All right, so we talked a lot about the detectors, the abilities of the detectors, analysis procedures. We'll just retouch again on some of the ACOMP benefits from those. We've shown a little bit about how reduction in cycle time can improve your cost, and it can also improve your quality of the product that you're producing because you know in real time what you're making and how to affect the process to avoid anomalies and then also drive the product, the values that are of interest to you. Efficiency, if you're not making off-spec product, there's less rework to deal with. But also, since we take the human out of the loop of sampling and collecting data and then running it to the lab, we avoid a lot of those interaction points where an employee has to go out, gather product from a hot environment, environment that has carcinogens quite often, or VOCs in the air. So we can reduce a lot of those overhead issues with health and safety and environment effects. So beyond that, I'd like to thank everyone for attending, and let's get into some questions from here.
Thank you, Mike. The first question we have, is it necessary to have all 4 detectors? What synergies does it bring to have all 4?
Well, as I mentioned in this presentation, the synergies of all 4 give you the whole aspect of molecular weight, intrinsic viscosity, concentration, and control. But also mentioned that we do not need to have all 4 detectors in every single ACOMP. If the application is specific to understanding just concentration and there's no molar mass to be measured, there's no reason to have molar mass detection. If there's instances where you're looking at, say, emulsions or inverse emulsions, the droplets from those emulsions will not respond well with your light scattering or refractive index devices. So we unfortunately cannot use them in those particular cases unless we do some additional processing of the sample to get it down to the parameters that you need for those particular types of detectors.
Thanks, Mike. The next question, is GPC available as an option, and how would that work?
We do, let's say, we don't exactly offer GPC as a offer with ACOMP, but we do have a lot of experience in integrating GPC with ACOMP. The nice part about ACOMP is that it's producing product from the reactor down to conditions that directly inject into a GPC system. We do have experience extensively with proving that GPC analysis is equivalent to ACOMP analysis, but we also like to just self-check ourselves and self-police that we're producing the product that we expect the customers to be more familiar with. So if you have a GPC system and you want an ACOMP system to produce samples, tell you what's going on in real time, and then take that sample directly and inject it into your GPC system, that's an integration aspect that we can work with you on.
Thanks, Mike. The next question, Please explain the measurement of gelation again. How accurate is it in determining the onset of gelation in the emulsion?
Okay, yeah, so we've seen quite a few instances where gelation is a big aspect of either inverse emulsion, where you're working with highly concentrated polymers and they start to interact or cross-link on each other. The aspect of looking at the viscosity and molecular weight, if you think in a gelation event, the cross-linking doesn't exactly change your viscosity too much because you're not changing the hydrodynamic volume too much. In the aspect of light scattering, taking two polymers and sticking them together, your molecular weight doubles directly as a result of that. So light scattering picks that up quite exclusively to the sensitivity of that thing. I can't say exactly with a value to say, okay, that you can say two monomers stick together, two polymers stick together to produce a gelation event. But yeah, it is exquisitely sensitive to the picking that information up.
Thanks, Mike. Next question: do the detectors foul or plug?
I would say, on a defensive side of things, that any detector, if it's not treated properly and not conditioned properly, is going to foul and plug up. The nice part about our ACOMP system is that it's automatically taking sample from the process, diluting it, and conditioning it with a solvent stream. So in our cases, we're dropping the concentration of the product from the reactor to, say, 1 milligram per milliliter or less before it goes to the detector stream. So the instances of plugging, fouling, damage to the instrument or something like that is pretty much nil in that cases, because we're actually taking the sample and purposely diluting it to the point where it does not have a plugging or gelling or fouling event.
Thanks, Mike. We're down to the last question, so if anyone else has questions, you can pose them using the Q&A feature or the chat feature. You mentioned particle size measurement as an additional detector. Are you currently able to measure particle size or particle size distribution of emulsions?
We've actually worked on that in the past. Again, we don't sell, like with the GPC systems, we don't directly sell GPC, we don't directly sell particle sizers, but we can work with you directly to produce a data stream that can give you particle size. The information that is gained from that is directly correlated to the values that you're looking to. So if you want a particle size distribution, if the detector produces that data, that's a data stream we can integrate in the ACOMP system and produce and hand back to you as well.
Okay. Well, that's it. We don't have any more questions, so at this time we're going to wrap up the webinar. I'd like to thank all of you for attending. I'll send out the recorded webinar as well as the PowerPoint deck early next week. And I'd also like to thank our panelist, Mike Drenski. Please get in touch with us if you're interested in discussing ACOMP for your particular applications. So thanks again.